This video is just tying together everything we've learned about inverse trig functions. Here we have a chart that summarizes the domain, range, intercepts, and asymptotes of all 6 inverse trig functions. We only really talked about the first 3. Honestly, those are the ones that we use the most. So I encourage you to pause the video and read over this whole chart. The key things to know are really just this right here. But as I mentioned in my videos on these 3 inverse trig functions, you can get everything you need from the graphs of sine, cosine, and tangent. So your need to memorize this really isn't there. But I also want to talk about how we can put these inverse function ideas together with regular trig functions. So we're going to find the exact value of each expression without a calculator, and these expressions are going to involve compositions of inverse trig functions and regular trig functions. So we have sine of arc cosine of 1/4. Starting on the inside, we have this arc cosine of 1/4. An inverse trig function always gives an angle. And previously, we were just pulling angle measures off of the unit circle. But we look at this number 1/4, and that is not a number that's familiar to us from the unit circle. So this is not just going to spit out an angle for us like it did in some previous examples. What this is going to do is this is going to give us an angle within a triangle. So I'm going to draw a triangle. We know that cosine inverse is only defined in quadrants 1 and 2. And this 1/4 is positive, so that means that our triangle is going to have to be in the first quadrant. And this is some angle theta. We'll say that this whole thing highlighted in yellow is our theta. Well, cosine is x over r. So that means 1 is our x and 4 is our r, and we can do Pythagorean theorem to find the third side of our triangle. Now, why do we care about finding the third side of our triangle? Is because ultimately then we want to find sine of this angle. And since we weren't able to get an explicit angle, we're basically looking for sine of the triangle. And for sine, we need the y over r. So we're going to do Pythagorean theorem here. Oh, 15 equals y squared, so y is going to be square root of 15, which does not simplify. So again, we want the sine of this triangle. So sine of arc cosine of 1/4. The sine of that triangle is going to be square root of 15 over 4. Let's try some more. Next, we have sine inverse of sine of 3 pi over 4. Notice that this time the inverse trig function is on the outside. So that means that our final answer in this example is going to be an angle. Let's start on the inside. Sine of 3 pi over 4. That is not an inverse trig function, so it should just spit out a number for us. And 3 pi over 4 is one that we recognize from the unit circle. Right, 3 pi over 4 is right here. That's the same as 135 degrees. So when I draw in my triangle, I'm going to have a 45-degree reference angle there. And the sine value of that triangle there is square root of 2 over 2. So this now becomes sine inverse of square root of 2 over 2. Okay, now we got to find the angle that sine ends up being square root of 2 over 2. I always like to do this example because students frequently make the mistake and they just cancel out the sine and the sine inverse because they're inverse functions and say, oh, the answer is 3 pi over 4. But that's not the answer because 3 pi over 4 is not in the range of sine inverse. Sine inverse is only defined from negative pi over 2 to pi over 2. So that answer of 3 pi over 4 cannot be correct. When we look at this, we have to use that pure definition of sine inverse where we're only looking in quadrants 1 and 4. The question is, what angle in quadrants 1 or 4 does sine have a value of positive square root of 2 over 2? Sine is positive in the first quadrant, and it has a value of square root of 2 over 2 when we have a 45, 45, 90 triangle. So we're going to get a final answer here. Make sure it's in radian of pi over 4. So it's really important. You just can't cancel out an inverse trig function with a trig function. You won't necessarily get the correct answer because of that restricted range. Next, we want to find tangent of arc cosine of u. You'll notice that on the inside, we have an inverse trig function, so we know that this is some angle. U is definitely something that I do not recognize on the unit circle, so this tells me that I'm going to have to create a triangle. Cosine inverse is defined in quadrants 1 and 2 only. That u is positive, so we're going to assume that cosine is positive and that we're going to be in the first quadrant. So this will be like some angle theta. Cosine is equal to u. We know that cosine is adjacent over hypotenuse, so that's going to have to be a u here and a 1 on the hypotenuse. It's the only way I can get u when I simplify. We need tangent of this triangle, and tangent requires the opposite side as well as the adjacent side, so we're going to have to find that third side, and we're going to use Pythagorean theorem to do that. 1 squared is equal to u squared plus y squared. Now I know this is going to look weird. Trust the algebra. This will be 1 equals u squared plus y squared. And remember that we're solving for y. So let's subtract u squared from both sides. 1 minus u squared equals y squared. And then we are going to take the square root of both sides. Now, typically, the plus or minus shows up in square root property, but think about it. Since we're in quadrant 1, the y value is going to be positive, so we're only going to have the plus. All right, so there's our triangle. And now, we want tangent of that triangle. Tangent of arc cosine of u is going to be equal to the opposite side, square root of 1 minus u squared over the adjacent side of u. I really like this type of question for an exam question, so I would definitely practice it.